Today we're going to take a look at the fundamental theorem of calculus. So we've been looking at definite integrals. Here's one example. And we've been interpreting this as area under a curve. So this function here is 2x plus 1. Function looks like that. Now we're only looking from 0 to 3. So that definite integral can be evaluated by finding the area of this trapezoid. So let's say this up here would be at 3, 7. And the area of the trapezoid would be 1/2 times 3 times the sum of the bases, which would be 1 plus 7. And that's equal to 12. Now the fundamental theorem of calculus allows us to evaluate this integral by using the antiderivative. So what we do is we first take the antiderivative of 2x plus 1. So we get x squared plus x, but we still have to worry about this 0 to 3. What we do is we first substitute 3. So we get 3 squared plus 3. And then we substitute 0. And find the difference of those two quantities. So let's see, this is 9 plus 3, which is 12, minus 0, which turns out to be 12, which is exactly what we got when we interpreted the integral as area. So the fundamental theorem is extremely helpful when we're evaluating functions like this. Let's go from -1 to 3, and let's just go with x squared. So if we're thinking about this as area, we know what x squared looks like. That's just a nice little parabola here. And we're only going from -1 until 3. So this area here. And the way that we've been calculating this area is by choosing to go with our left endpoint or our right endpoint, setting up a summation, using the base times f of whatever we were using, the left endpoint or the right endpoint. And then when we were done, we would take the limit as n goes to infinity, and we'd have our area. Now with the fundamental theorem of calculus, it looks like this. We make this x, cubed, 1/3 in front. We're evaluating this from -1 to 3. So first we plug in our 3. Then we plug in our -1. Here, this is 27 divided by 3, which is 9. And this turns out to be plus 1/3. So we get 9 and 1/3, or 28/3, as the exact area between -1 and 3, and between y equals x squared and the x-axis. Okay, so there's one condition to the fundamental theorem, and that is that f must be continuous on our interval. Then the definite integral from a to b is equal to big F of b minus big F of a, where big F is our antiderivative. Derivative. And just one thing to keep in mind here is that our definite integral represents area under f of x from a to b only if our function is above the x-axis. We'll get into what happens when our function goes below the x-axis very soon.